Hi there, and welcome to another fun time with Coach Powers. Chem Coach Powers here, bringing you some physical science, chemistry style, or is it chemistry, physical science style? We're talking about some cool concepts today. One of them is called Le Chatelet's principle. Super, super cool stuff. The other one is something basically which is what kind of things are affecting the reaction rates. Okay, so we're going to look at how reactions are affected by different situations, and then we're going to talk about something called Le Chatelet's principle, which is just a really cool concept here. All right, so let's start with our objectives. Reaction rates and equilibrium is our section 7.4. We're going to describe 6 factors affecting the reaction rate, and then we're going to explain what chemical equilibrium is in terms of forward and reverse reaction, and we're going to talk about something called Le Chatelet's principle. So collision theory, basically the idea behind chemical reactions is that in order for a new chemical to be formed, these two substances must have collided at some point in time. They have to contact in order for those atoms to get into a place where they are close enough where they can have an attraction that's strong enough to make them bind. Okay, so you have to have chemical reactions that will bring you into contact. And so the more collisions you have, the more reaction you're going to have. And that's basically the idea here. Anything that increases contact between particles will increase the rate of the reaction. Okay. And they must collide, not only just collide, but collide with enough energy. If they don't have enough energy, the reaction won't take place. So what are our ways to increase the rate of reaction? First of all, we can change a reactant that's more reactive. And so if I want to see a particular reaction speed up, maybe, for instance, I had lithium in a substance, put lithium in water. Well, let me instead put sodium in water. And then I'll have a reaction that takes place much faster. Now, this is going to change the overall products, but the reaction is going to take place much faster because sodium is a much more reactive element than lithium when it comes to reacting with water. Our second one, if I increase my concentration, okay, so it's increase. If I increase the concentration or the number of molecules, then I'm going to end up getting more collisions, right? And so if I use a concentrated acid and I put some acid on zinc, and if I use concentrated acid, it's going to start bubbling, the zinc's going to dissolve, and it's going to disappear. But if I use a weak diluted acid, not just weak, but let's say diluted acid, then it's going to end up slowly reacting, and eventually, it may not disappear, right? And so the concentration of my material, my reactants, is going to affect how fast that reaction takes place. And then I have surface area, okay? If I increase my surface area, I am going to have a faster reaction. Now, this is what happens in grain explosions. If you guys have ever heard about a grain mill, like where they take wheat and they're crushing it up and turning it into flour, places like that, if they are not very, very careful, they produce this fine powder that gets in the air. And that fine powder will actually explode if a spark comes off. So these people that work inside these mills, they have to make sure that they're always grounding themselves out. And sometimes they'll walk around places with actually, metal connections between their body and some sort of ground source so that they don't build up static electricity, cause a little spark, and cause the entire grain factory to explode, because that has happened many times in the past. And so if you took some wheat and you actually burned it, and I'll show this to you guys in class. If I tried to take some wheat and burn it, it won't do anything if it's sitting there as a pile. But if I spread it out into a powder, get some fire. It's pretty cool. Next one, pressure. The gas inside a piston. Okay, again, we're looking for increases, right? If I increase the pressure, I'm increasing these things. I'm putting more pressure, so they're getting closer and closer. They're colliding more often, and so that's going to increase my reaction. And so if you have a gasoline car and you are pushing the piston closer, you're taking that gasoline that's just been aerated and you're pushing it closer and closer and closer and tighter together. Eventually that spark is going to be able to ignite it and give a lot of explosive power with a fast reaction. If you didn't have that piston closing in on that gas, it wouldn't be a very powerful explosion. And then increase in temperature. If I have an increase in temperature, for instance, with yeast, if you guys have ever, put your yeast in your dough and you're watching your dough rise, you do that at room temperature, right? You don't put that in the refrigerator because the yeast is going to rise faster at a higher temperature. Yeast is going through a chemical reaction where it's breaking down sugars and it's creating carbon dioxide and water. And the carbon dioxide is the gas that makes your bread rise. And so yeast at room temperature is going to react faster than yeast in a refrigerator. If you want to stop the reaction, stick it in the refrigerator, right? And then we can add something called a catalyst. Now, we've been doing catalysts as our bell work, for this entire semester. Catalyst is something that increases the rate of the reaction, gets the reaction started a lot of times. And that's why we call it catalyst each and every day when we start you with bell work, is because we're trying to get your juices flowing, get you started, right? We're trying to get that reaction of you interacting with material a little faster. Okay, so a catalyst is a substance that increases the rate of the reaction. It is important to remember that catalysts are not changed by the reaction. They're still left over at the end, and they can be reused over and over and over again. That's a pretty cool thing about catalysts. A couple of examples. We have catalytic converters, and we have some enzymes. I want to show you some of those examples here. Here you can see a catalytic converter. The catalytic converter basically is usually going to have platinum or palladium inside, sometimes a mixture of both, and that's a place where the excess gasoline that didn't quite combust fully can kind of sit there, and while it's sitting on the tiny little holes that are filled with platinum and palladium, then that allows for the reaction to complete, and it can form the carbon dioxide and water vapor that you would have from your exhaust. And so catalytic converters actually are pretty expensive. Sometimes they're stolen out of cars because platinum's a very valuable metal, and so you have this valuable metal here, but what it does is it allows for the reaction to go to completion, and it makes sure your exhaust is much, much cleaner than if you didn't have a catalytic converter. And so that's part of your emissions system. It makes your exhaust air a lot cleaner. Now let's look at these two graphs of catalysts or reactions. Here's a reaction, right, that's taking place, and so it's going up and then coming down. This reaction is uncatalyzed. In other words, there's no catalyst there. And so it's got to get to a certain energy of activation. In this case, it's the energy of activation of 75 kilojoules per mole. Well, what happens if I put a catalyst and I involve a catalyst with it? Okay, if I take, in this case, this is decomposition of hydrogen peroxide. You may have seen something like elephant's toothpaste. We'll do that too. If we take this if we take this hydrogen peroxide and we put a chemical in it, we can get this reaction energy to go down. So it can go down from a 75 all the way down to a 58. That's much less energy per mole, right? 58 kilojoules per mole versus 75 kilojoules per mole. And this chemical that we put in there, it can be reused. It's not, destroyed. But look at this. If we take an enzyme, and this is, they have things inside your body. You have some of this inside your body. It's called catalase, and it's in certain cells of your body. And sometimes your body needs to break up hydrogen peroxide that's in your body, and it will break down that energy of activation all the way down to a 4 kilojoules per mole compared to 58 or 75, right? So this enzyme can just do a great job of breaking stuff down and making the amount of energy required for something to take place really low. And yeah, it's pretty cool to see what catalysts can do. And again, they can be reused in the reaction over and over again. This is an enzyme, versus the chemical, right? And this is a particular type of enzyme that can have a certain shape. Notice how the shape of this purple part matches perfectly the shapes of the yellow and the orange part. Well, this catalyst is the enzyme, okay? So an enzyme is basically considered an organic or a biological catalyst. And it will, and these are proteins, it will, in this case, make the two substrates or the two chemicals come together and form a single product, and then that single product is going to go off into your body to do something else, right? So this is happening inside your body all the time. You've got enzymes that are breaking things up, but you've also got enzymes that are putting things together and giving you some new products that your body needs. So catalysts are used inside your body. It's pretty cool stuff. All right, now let's talk about equilibrium. Equilibrium is this concept of equality, right? I got to have some sort of balance. That's what we talk about. You know, if you are spinning around in a circle and all of a sudden you feel dizzy, your equilibrium is out of balance, right? You feel, well, that's what equilibrium is. Equilibrium is just thinking about the idea of balance and how do we maintain balance? Well, if I have a single arrow pointing in one direction like this, it means that the reaction is just going in one direction. The reaction goes to completion. It doesn't go back in the other direction. So for instance, if I take a match and I light that match, it's going to burn, turn into carbon, and it's not going to go back and turn into a match, okay? Same thing with a rusting nail. The iron is getting turned into iron in the presence of oxygen, getting turned into iron 3 oxide, and that is going to be a new compound, and I can't take the iron 3 oxide and see that go back and turn into iron, okay? So some of these reactions are not reversible per se, but some reactions are reversible. In fact, actually most reactions are reversible to a small degree, where you're going to end up having the reaction proceed in one direction mostly, then it kind of goes back this way, and eventually it finds a place where the reaction is taking place simultaneously in both directions. And that's why we use a double arrow here. Sometimes you'll see the arrow, you know, with 2 heads like that. Sometimes you'll see, I like to draw it like that. Sometimes people will draw them with the 2 arrows. Whoa, come back. 1 arrow there, 1 arrow there kind of thing. But this is a reversible reaction. And a good example of this is what's happening inside your Coke can or your Coke bottle, right? Here we have H2CO3. Oops, sorry, those are not subscripts, are they? Those should be little subscripts. H2CO3. And then this is CO2, H2O. You take this is called carbonic acid, the hydrogen carbonate, and you take that dihydrogen carbonate and dihydrogen carbonate, and you take that and it's in an aqueous form right now, right? So it's dissolved in water. That is going to be making carbon dioxide, those little bubbles that fizz out, and then some water. And sometimes that is actually happening in exactly the opposite direction at the same time. Some of the carbon dioxide and water are combining together and they're forming new H2CO3. This is happening in both directions over and over and over again. And this reaction is something we would say is at equilibrium. In a closed soda bottle, this is just taking place in one direction, okay? Or in both directions. It's going back and forth. It's hit equilibrium. It's state in which the rate of the forward reaction is equal to the rate of the reverse reaction, okay? Think about it like a football game or a soccer game or a volleyball game. If you've got somebody that is going onto the field, you've got to have somebody coming off of the field, right? And that's kind of like what these equilibrium reactions are like. Some are going on, some are coming off, okay? And you have to have an equal amount in both directions. The game still goes on as different players are going in, and you're just getting an equilibrium state. Okay, so here's a picture of this. I can see that here in this picture, I've got an equal amount. Look at my number of arrows going out. I've got 2 arrows pointing out, and then I've got 2 arrows pointing in. So I've reached equilibrium. They're just kind of showing that by the arrows there. Carbon dioxide going out, carbon dioxide coming in, forming an equilibrium. But in this case, when I open the cap, then I've got more going out than going in. And so now I no longer have equilibrium. Okay, I'm no longer at equilibrium because now I don't have the same number of particles going into the liquid as I do have coming out. Same particles making carbonic acid as are making carbon dioxide and water. Okay, so that is an example of this is equilibrium. This is not equilibrium, right? Okay, so there's a term called Le Chatelier's principle that predicts the changes in equilibrium. Okay, and what I want you to know about Le Chatelier's principle is basically it is a response to stress. When a system gets stressed with some sort of influence, pressure, temperature, things like that, then it's going to react to relieve that stress. Just like you might try to relieve stress You know, you're getting all stressed out. You might do something to relieve the stress. Well, chemical systems do the same thing. Okay. They are going to respond. Okay. The systems are going to respond. If they're in equilibrium, they're going to respond to minimize the change. And that's what Le-Chatelet's principle is all about. Okay, so I'm going to look at three different things here with you: temperature, pressure, and concentration. We can look at other things too, but right now we're going to look at temperature, pressure, and concentration. And we're going to see how these things are affecting the reactions. Okay, you can look at these in more detail if you want, but we're going to talk about them together here. Okay, so let's look. Here's the definition of Le-Chatelet's principle. If a change is made to a system in chemical equilibrium, the equilibrium shifts to oppose a change until a new equilibrium is reached. That new equilibrium will be reached over time, okay? And if I look at this particular chemical reaction, this is called the Haber process, and it's used to make ammonia. This is a really fascinating chemical process. You know, that was invented by a very fascinating person, Fritz Haber, who is not a good person, I will say, if I can be a judge of personality and what you do in life. He was a World War I scientist, and he actually is responsible for, creating a lot of the poison gases that were used in World War I. He was taking French prisoners, and he was just testing, chlorine gas on them and just killing them, high and high, willy-nilly. This is not a good guy. However, a third of the world's population actually is able to survive today because of this process, because it makes ammonia, which we use for fertilizer. He actually got the Nobel Prize for discovering this process the same year that he was coming up with weapons that were killing, thousands of people. Really controversial. And he loved his home country. He was a German, and he was just trying to, help his country win the war. And he just justified doing a lot of really horrible atrocities for that. But of course, that's what war is all about, isn't it? It's a lot of horrible atrocities. But anyway, he's also not a very nice guy on a personal scale either. If you ever look into his story, his wife Clara, and go look it up. It's pretty sad. All right. Anyway, so this reaction of making ammonia is going to be done under high pressure and a low relative temperature. That's where it's going to be the best at producing the most ammonia. Okay, and so let's look at these a little bit in more detail. If I am changing my temperature by increasing the temperature, it's going to then favor a reaction that will absorb energy, right? It'll take away the energy. So if I increase, the temperature with a little up arrow, then the reaction is going to try to decrease the temperature, okay? For pressure, if I increase the pressure, then the reaction is going to do something to try to decrease the pressure by making fewer molecules of gas. Okay, if I increase the concentration, then the reaction is going to do something to try to decrease the concentration. So each of these responses to pressure are what we're talking about when we talk about Le-Chatelet's principle. The equilibrium, if we use the term equilibrium shifts to favor the reactions, that just means that we're saying more reactants are forming. We also sometimes say that it shifts to the left. That means that more reactants are forming. Okay, so if I say shift to the right, more product. Shift to the left, more reactants. That's the terminology we use for shifting. Okay, so now this is a video, and I'm going to go ahead and play this video, and you can just listen to the video while it plays. But this is a good illustration of Le-Chatelet's principle with these three things: pressure, concentration, and temperature. So I'm theoretically going to play that video if I hit the right button. Okay, so we want to talk about the factors that affect equilibrium. Here we are going to look at the effects of pressure, concentration, and temperature, and how when you change one of those things, you're going to cause a change that will reduce that other thing. So anyway, this first reaction here, we've got nitrogen and hydrogen reacting to form ammonia gas. And if we increase the pressure on this, and in this case, we're allowing some of the hydrogen or some of the pressure to increase, it's going to try to make molecules that will decrease the pressure. So it went from 3 molecules
to, or actually 4 molecules to 2 molecules. And so it reduced the amount of pressure because it reduced the amount of molecules and it reduced the total collisions. Now we want to talk about concentration. Here in concentration, you can see that if we add some hydrogen gas here, it's like, okay, well, what can I do to reduce the hydrogen gas? Well, I can make some more ammonia in this case. And so it added hydrogen, and then what happened is it took away the hydrogen. So it's basically balancing out. Whatever you do on one side, it's balancing it out to reduce it. So it's acting to relieve stress in a situation. Okay, so here we have temperature. Now these are exothermic and endothermic reactions that can occur. And then this first one, you can see that this is endothermic, meaning that it absorbs energy. If you go to the right, you're going to absorb energy. And so here we went from having these extra ammonia molecules, and it broke them up into smaller molecules. Why? Because if it's absorbing energy, it's going to want to react to create energy. And exactly the opposite. If you have a reaction or a part of a reaction that's actually giving off energy, then it's going to try to absorb the energy, and so it's going to react in such a way to do that.
Okay, so hopefully you got a good feeling for some of that. Don't worry about the details there so much, because in chemistry, you're going to see that a lot more in detail. But what I want you to see there is that there's always a reaction, and it kind of gives you a nice little visual picture as you look at those different molecules working their way through. Okay, so here is that chemical reaction. And, if we were to balance this chemical reaction, we could put a 2 in front of that, and then we'd want a 3 in front of that. And so now we've got a balanced chemical reaction. This is the Haber process again, right? Which way is the equilibrium going to shift due to the following changes? So if I add nitrogen, then I'm adding more of that. So the chemical equation wants to get rid of it. And so it's like, well, I've got too much nitrogen. What can I do to get rid of the nitrogen? It can tie it up in ammonia, right? And so it's going to shift to the right. If I add NH3, well, now I'm adding more of this stuff. And it's like, what? I don't want that. I need to stay balanced. I need to stay in equilibrium. And so it's going to take that NH3 and it's going to turn it back into the N2 and the H2. If I increase my temperature, okay, well, if I'm putting heat in the system, it's like, whoa, I don't want more heat. I've got to change it so I can get rid of my heat. And so going to the right makes heat. If I add heat, it's going to shift to the left. And so I'm going to be making, if I add heat, I'm going to be making more nitrogen and hydrogen. If I increase my pressure, now look over here, I've got 1, 2, 3, 4 molecules on this side, and I've only got 2 molecules on this side. So that means I have more molecules on my left side of my reaction than on my right side, right? On my products, I have less than on my reactants. If I increase my pressure, it's like, what can I do to reduce my pressure? And so it's got to be like, well, I could make things go to the left side. If I can make fewer molecules, that's going to reduce my pressure. And so in this case, with increasing pressure, it's going to move in the direction to the right side, because that way it can go from 4 molecules to 2 molecules. And that's a much more favorable situation to relieve that stress. Isn't that cool? All right. So let's look at this question. How can we use Le-Chatelet's principle to favor the product? So this is what Fritz Haber was able to do. Basically, nobody was able to figure out what was going on. Germany had run out of saltpeter. They were going to Chile and they were mining the Chilean saltpeter. The Allied forces had stopped them from doing that. They basically created an embargo so they couldn't get that back over to Germany to create more weapons. And so, it'd be nice to think, oh, Fritz Haber, he wanted to make fertilizer to make the world have more food. No, he wanted to make the ammonia so he could make the ammonium nitrate to make the saltpeter, basically make weapons. He was making this stuff to make weapons so Germany could kill everybody and win the war, right? Well, so yeah, so much for the, great thing that he was trying to do. But again, we got lots of fertilizer out of it. Now our population and our world is able to, survive because we have enough food. Anyway, he came up with this process in order to make this fuel. And what did he have to do? It was very hard to do, but he finally figured out a way to make the products become favored, to make more of this stuff. But what did he have to do it? Well, he had to make sure that you were continually getting more of these reactants. So he created a cycle. So any leftover nitrogen and hydrogen were getting dumped back into the reactant side, so you could always get extra of the reactants. He also increased the pressure, right? Because again, if you increase pressure, it's going to try to create a system where it is shifting to reduce the pressure. So it's going to be shifting over to the right. And so he put this under high pressure, like 1,000 atmospheres, I think, or something like that. So I don't know what it was, but it's really, really high pressure. And then he also lowered the temperature, okay? Because again, lowered the temperature is going to shift it to make more heat. And so it's going to shift to the right. Well, and I say lower the temperature, but you might be looking at that. It's 932 degrees Fahrenheit. This is really hot, but it's lower temperature relative to what it could be if you were at a higher, in that high pressure environment. It could be much higher temperature. So anyway, good stuff. I hope you guys are having fun seeing how all of this stuff relates, because it all relates, right? So now can we do what we set out to do? Our objectives. Let's go look at those objectives again real quick, because, boom, we want to know what we learned, right? So can we describe the 6 factors affecting reaction rate? Yeah, we can, right? We've got things like increasing the temperature, increasing the pressure, increasing the concentration. We have increasing the surface area. We have catalysts. And changing the type of chemical that it reacts with. Got all 6. Can we explain the chemical equilibrium in terms of forward and reverse reactions? Equilibrium goes in both directions, right? A chemical reaction at equilibrium will go in both directions, and once it's in that state of equilibrium, you've got things happening at an equal rate. And then you learned about Le Chatelier's principle too, bonus, where you get to see how affecting, adding one thing is going to change it, and it relieves stress, and that's just too cool. All right, well, we are awesomely chemicalized, chemistryized. We know more chemistry now, and it'd be cool if I had a cool word like chemicized that actually made sense, but I don't. Anyway, have an awesome day. Thank you guys for listening. I hope you enjoyed this, and we will catch you on the flip side. God bless you. Be kind to one another.